Hello, good morning, actually good afternoon or evening, whenever you're watching this. Um, so today is November 30th, and we have all classes have finished assignment 9, and so I'm cool to make this recap video. Today we're working on, first off, we have a few messages to start with. Each class at this point has essentially 8 days left of instruction. Um, that's including all the way up to the last day, 8 days. So within that time, we're finishing off assignment 9. We're finishing off notes on entropy. We're finishing off assignment 10, work and heat, notes on the interior of the Earth, and then our final. So within 5 days, or within 8 days, we have 5 things to cover, more or less. Um, so it's going to be a little bit packed. That should be fine. To start, let's look at the agenda real quick. Now, assignments 7 and 8 were graded during Thanksgiving break. So if you are not satisfied with your grade, feel free to update it. If you have things you need to update it, just let me know and I'll recheck it and update your grade for it. This Friday, December 4th, I will be posting up our final, both parts. The two parts are your pretest, which will be retaken this time for a grade, as well as a secondary part, which is a model of the Earth that you will build based on several sets of data. I'll explain more of that on Friday. I think that's about it. On Tuesday, even periods will cover entropy. On Wednesday, odd periods will cover entropy. On Thursday, even periods will cover assignment 10. And on Friday, odd periods will cover assignment 10, leaving us for next week, assignment 10, as well as the notes on the interior. So that's about that. I think that's going to be it. Right. This Friday is an odd professional development day, and assignment 9 will be due on that Friday as well. So make sure it's all ready. Now, what do I need from you guys as far as assignment 9 is concerned? Just to recap, you guys are working on the vocab yourselves, the math on the energy required by iron, copper, and aluminum yourselves, as well as this conclusion part for the diffusion of energy yourselves. In class today, we worked on numbers 5 through 6, 5 through the rest. I took a little bit more time than expected because I did have several tangents on backdraft and several other examples. Now, looking at an image of a thermos, we decided at a random poll for which piece here was the most important in your opinion, and the results were spread out, but for the most part, we were picking insulated support, which is not bad. Insulated support, silvered surfaces, and the vacuum were my top three, and as long as one of those were picked, I was feeling fairly comfortable with your understanding of how this flask works. And so the idea behind a thermos is that we're preventing heat loss, we're preventing conduction and convection radiation from affecting the temperature of our liquid, right? We prevent heat loss through radiation by trapping that heat inside of it. So the vacuum, that silver surface, all of that works to reflect heat back into our liquid and kind of create our convection current here. And so temperature is always maintaining its desired temperature. So you have like pour some hot coffee into our thermos, that heat reflects back into the liquid, and so our convection current forms and it maintains itself because we're preventing any heat loss through radiation. Now, for number 6, we're editing this image to kind of show how conduction, convection, and radiation all occur inside this lava lamp. And so if you've ever had one, you know that it's warm on the outside. And so that's radiation. The heat of that lamp radiates outwards in 360 degrees. The convection current raises the oil, right? It heats up that oil, which rises. It cools down and it sinks and it starts all up again. That's the convection current. And then conduction That's just heat directly being transferred. That's the heat lamp down there, right? Heat is being directly conducted into our liquid, into our glass, and so it's just very, very hot overall. The examples that I spent some time with today were backdraft and a convection oven, right? In a convection oven, it's not liquid. There's no liquid involved, but it is air. So convection runs in both gases and liquids. Remember that. In an oven, the heat warms up the bottom of our uh, air, which rises, then it cools, and so that cycle forms and allows us to bake things inside of the oven. In our oceans, right? That the sun warms up the equator, right? All that water at the equator heats up, rises, and so it flows. The cold water at the north and the south sinks back down, and so we have a cycle. We have a convection current along the coasts. And so this is what we spent a good chunk of our time on. I also had a few interruptions today with regards to just Zoom dropping my call. My computer is dropping, but that's a thing. The rest of this were answered through polls. And so we're talking about how liquids and other materials spread, how they diffuse, right, throughout a gas versus a liquid. And so the diffusion of matter and energy in a liquid is typically slower than in a gas, right? If I have two gases and I want to mix them, that happens a lot faster than if I took two liquids and I mix those instead. The particles in a liquid are way slower than the particles in a gas, right? Break down a gas and a liquid into individual particles. The particles in a liquid are still kind of just floating down at the bottom of a cup, whereas the particles of a gas are energized. They're bouncing around the walls. They move very, very quickly, which means that energy and matter and everything like that can be transferred very, very quickly. Now, the second question here is what factors can cause diffusion to go faster? The idea here is how do we make sure our two liquids spread evenly? And so the ideas we got in class are mixing, stirring, blending, shaking. It's a very limited list of ways we could mix liquids. And one thing that we got, and the thing we're focusing on, is that warmer things tend to mix faster. Okay, we go ahead and watch this video here. And it's a video of just 3 glasses of water. One is hot, one is room temperature, and one is cold. I spread some food coloring into each of them. We just take a note of how they diffuse. In this hot cup, it's spreading out pretty quickly. Not even 5 seconds would pass and my cup is green. The room temperature one, maybe 6, maybe 8 seconds before it's all gets to be green. And with the cool temperature one, it's still going. It's still very much in a drop kind of form. And so we just kind of decide how that relationship works. So as far as it goes, hotter temperatures essentially mean we have faster diffusion. Go ahead and move this up front. As far as the rest goes, mixing, stirring, all that stuff will still make sure your other liquid is diffused properly, but the hotter temperature is what I really want to focus on because that's chemistry. If we want chemical reactions to occur, we want to have faster, we want to have these chemicals to be, we want these chemicals to be hot then, for those reactions to occur in a timely fashion. The rest of this is up for you to answer, right? So go through it, answer that on your own. And that's pretty much it as far as this recap video goes. Try to spend your time in Zoom. But if you have questions, feel free to message me, right? Schoology, email, Remind even. Speaking of, I just got a Remind message. So if you have questions, comments, or concerns, let me know. Otherwise, this assignment is due December 4th. That is this upcoming Friday. So I'll see you all later. And I hope you guys have a great rest of your day. Bye-bye.